everyone, and welcome to The Explainer. Today, we're unlocking the hidden systemic mechanics behind the circular economy, and specifically how the 4R framework actually works. We're going to look at some truly fascinating engineering research that proves why, right beneath the surface, this entire framework is really just a masterclass in energy preservation.
Okay, let's dive into this. Here is our 5-part roadmap for today. We'll start with the take, make, dispose trap, then enter the circular economy, explore the 4R framework hierarchy, uncover the hidden energy cost, and finally, discuss a just and fair transition.
Starting right off with Section 1, the take, make, dispose trap, or our linear problem. Historically, our traditional industrial model has relied on a really dangerous assumption, and that is the idea that natural resources are just infinite, and the Earth can absorb endless waste. So let me ask you this directly. What actually happens to your old smartphones? You know, when a phone gets damaged or it just gets a bit too old, our linear economy's default setting is straight up disposal. We extract raw materials using highly energy-intensive processes, manufacture the device, and then we just throw it away. But as natural resources become increasingly scarce, and frankly a lot harder to extract, the energy required to get them absolutely spikes. So this model isn't just bad for the environment, it's economically costly and completely unsustainable.
There is a stark contrast between a broken straight line system and a regenerative continuous loop. In our current linear take, make, waste model, raw energy goes in, products are consumed for a really short amount of time, and it all just ends up in a landfill. There is massive energy leakage every step of the way. Now, contrast that with the continuous loop of a circular economy. In this kind of restorative system, the waste from one process intentionally becomes a highly valuable resource for another. Products are designed right from the start for a long life, easy repair, and disassembly. It's an entire system upgrade aimed at closing the loop and preserving that recovered energy flow.
Moving right along to Section 2, enter the circular economy and decoupling growth from consumption. The core objective of this massive paradigm shift is decoupling economic growth from resource consumption. It basically replaces the traditional end-of-life concept with continuous resource circulation, keeping materials and energy in use for as long as physically possible. And to make that shift, the circular economy relies on 3 overarching system-level principles. First, you have to design out waste and pollution right from the drafting table. Second, keep products and materials in use. And third, actively regenerate natural systems. What's incredible is how perfectly this all aligns with the United Nations Sustainable Development Goals, specifically SDG 12, which mandates responsible consumption and production. By redesigning our systems this way, we minimize environmental degradation and actually promote long-term global sustainability. Which brings us to Section 3, the 4R framework hierarchy, which is a strict order of operations. Let's move to the 4Rs and see how this builds, because I really want to emphasize that these aren't just feel-good eco buzzwords. They represent a strict, prioritized order of operations for efficient resource management. Step 1 is reduce. This is absolutely paramount, minimizing raw materials and energy right at the source. Step 2 is reuse, where products get used again for the exact same purpose without major processing. Step 3 is recycle. Now, notice this is lower down. It converts waste into new materials, sure, but it requires a lot of extra energy to do so. And finally, step 4 is recover. This is the absolute last resort, where we extract energy from waste only when no other options are on the table. When you view these 4Rs through the lens of energy impact, a really fascinating reality emerges, and it's kind of the major aha moment of this whole concept. This framework is fundamentally about preserving energy, not just physical materials. Reduce yields the highest energy savings simply because you aren't producing anything at all. Reuse preserves all the energy already spent making the product in the first place. Recycle definitely saves energy compared to extracting virgin raw materials, like, for example, recycling aluminum takes vastly less energy than mining bauxite, but it still requires a ton of energy to melt and reform the metal. And recover, through methods like waste to energy, reclaims a small fraction of energy, but it's by far the least efficient. That flows perfectly into Section 4, the hidden energy cost, looking at embodied versus operational energy. Now, what's really interesting here is if you challenge yourself to look at the everyday items in the room around you right now, not just as stuff, but as physical collections of embedded energy, there are 2 main types at play. First, you have embodied energy. That's all the power used to mine the metals, manufacture the parts, and physically transport a refrigerator to your kitchen. On the other hand, you have operational energy. This is the electricity consumed when you actually plug that refrigerator in and use it over the years. In our traditional linear systems, discarding a product early means all of that embodied energy, the manufacturing, the transport, the whole shebang, is entirely lost. To ground this academic framework in our daily lives, let's look at a super relatable analogy. If you use a reusable water bottle, you are prioritizing the reuse step. You are completely preserving the existing embodied energy of that metal or hard plastic. If you use a disposable plastic bottle and recycle it, well, yes, you are keeping material out of a landfill, which is great, but the recycling process itself requires additional processing energy. It has to be transported, melted down, and remade. And that is exactly why reuse sits functionally higher on the hierarchy than recycle. Okay, time for a quick, slightly provocative scientific reality check. While circularity is absolutely the goal, we are still bound by the thermodynamic limits of our universe. Governed by the first and second laws of thermodynamics, a 100% perfectly closed circular system is actually physically impossible. In every single physical process, whether it's manufacturing or recycling, some energy is inevitably degraded and lost as unrecoverable heat, and materials physically degrade over time in a process known as downcycling. So we can't achieve utopian perfection, but we can dramatically optimize the system we have. And finally, Section 5, a just and fair transition, focusing on the social reality. So the crucial point is this. We've talked a lot about thermodynamics and energy flows and materials, but shifting global economic models away from a reliance on fossil fuels and linear consumption has massive, immediate social implications for real human beings. A successful circular economy has to balance environmental sustainability with social fairness. We have to proactively manage this shift. That means actively reskilling and upskilling workers who will be displaced from traditional fossil fuel industries. It means aligning with SDG 7 to ensure equal access to affordable clean energy so that low-income communities aren't penalized by sudden pricing shifts. And it means ensuring that the new jobs created in the recycling, repair, and renewable sectors are actually decent, safe, and fairly paid. We'll leave you today with this thought. If science tells us a 100% perfect circular economy is physically impossible, how do we ensure the messy, ongoing transition is actually fair for everyone involved? The 4R framework gives us an incredible technical blueprint for our materials and energy, but it is ultimately up to us to build the social framework to support the people navigating this huge change. Thank you so much for joining this explainer, and we really hope this sparks a brand new way of looking at the resources and energy all around you. See you next time.